I'm going to talk about low-dimensional data structures, and we are trying to understand neuron scaling laws. Okay, so first I want to acknowledge my brilliant collaborators. They are my PhD student, Alex, who just graduated and joined Google DeepMind. And Zai Ming is a current postdoc at Georgia Tech. He is here and he will give a poster in the afternoon. So please feel free to talk to Zai Ming. Rongjie, everybody knows him, and Alex is a student of Rongjie. Okay. So everybody knows GPT and probably tried it. Okay. And so what does GPT stand for? It stands for Generative Pre-trained Transformer. So you can see that the key architecture in GPT is transformer. Okay? And instead of using it as a black box, can we understand a little bit more about transformer? So, and my student Alex brought this paper into my attention. So in AI, there is a common belief saying that larger AI models trained on more data tend to perform better. How better it is, can we give a mathematical quantification? So in the paper of neuron scaling laws for large language models by OpenAI, they reported the scaling between the test error and the several key parameters. So those are the data size. How many tokens are we going to use to train the model? And also the number of parameters, how many parameters there are in the model. So they did a log-log scale between the error, which is the cross entropy on the test data, and the data size and the number of parameters. So interesting, they find a linear plot in log-log scale. And they did a lot of experiment in this paper. This scaling is almost everywhere in language models. Okay? So about this neuron scaling law, right? So if we see linear plot in log-log scale, it means that the error scales with respect to data size and the model size in a power law, right? So if you have a power function and then you take a log on both sides, and then the power comes down and you get a linear plot, okay? And the important quantity in this power law is the power, which is the slope in this log linear plot. So the power determines the rate of convergence, okay, which is very important. And for practical applications, it's very important it's very useful to understand the power. Why? Because those practical models are trained on really large data. So with billions of pixels, you can see 10 to the 9 billions of pixels. And the model size is also pretty big, right? So if you have an understanding of the neuron scaling law, then you can train on small models and have a pretty good understanding about the performance on larger models. Okay? So we're trying to understand a little bit more about the neuron scaling laws. Okay? So when we look at the power law, the closest mathematical theory we can think about is about the approximation theory and the statistical estimation theory. So which I'm going to start with a theory for feed-forward neural networks. Okay, so the left panel has approximation theory given by Yarosky in 2017. Well, he constructed a feed-forward neural network with ReLU activation function to approximate holder function as holder function on the unit cube. And then he gave the approximation error, which scales with respect to the model size. Capital N is the number of parameters in the model, okay? And it satisfies a power law, while the power is negative S over D, while S is the smoothness of the function, and D is the dimension, okay? So the right panel contains the regression theory saying that in practice, you're going to get a lot of training data with xi, yi pairs. And then suppose you get a global minimizer, and then the mean square error is going to scale with respect to the number of samples, little n. In a power law, well, the power is given by the squared error is like negative 2s over 2s plus d, well, s is the smoothness of the function, and d is the dimension. Okay? So those two theories have been established, but they all have the problem of curse of dimensionality. So if you have a really large dimension, capital D, for example, 1000, you plug in, the error actually decays pretty slowly. Okay? So the key or the common belief for the success is that real data usually have low dimensional structures. So for example, if you look at this image data set, which contains image of the same statue taken from left, right poles, up, down poles, different lighting direction. So every image actually can be parameterized by 3 parameters, which are the pose parameter and the lighting direction. And every image has about 4,096 pixels. You can think them as vectors in 4,000 dimension space, but they are parameterized by 3 intrinsic parameters. So this picture is taken from a paper in Science in 2000, which initiated the idea of manifold learning. Well, we can model data as samples on a low-dimensional manifold. Well, little d is the intrinsic dimension, and the capital D is the ambient dimension. Okay? So when we have a manifold structure, then actually when we do machine learning, we should respect the geometric structure such that if you look at the distance of 2 points, we should use the shortest path distance. And locally, we should look at the tangent plane because tangent plane contains information about the local geometry. Okay? So how about real data? Besides those simple examples, actually real image data also have low dimensional structures. And so I'm taking a result from Tom Goldstein, who graduated from UCLA. So they did like numerical experiments to estimate the intrinsic dimension of image data, such as the MNIST, which is the smallest data set in his experiment. And then also the largest one is ImageNet. So MNIST has about 700 ambient dimension, and ImageNet has about 150,000 ambient pixels. Okay, and then so he estimated the intrinsic dimension, and then actually showed that MNIST has intrinsic dimension about 10. You can think the intrinsic dimension as the dimension of the local tangent plane on the manifold. And ImageNet has intrinsic dimension about 45 for such a big data set. And he used the MLE method developed by statistician. Okay? And using the same method, my student Alex estimated the intrinsic dimension on the token embedding of language data set. So here we tried 4 language data. Tiny story is an AI-generated children's story, which is like this. So it's pretty simple, but it has the right grammar over there. Okay? And Open Web Tech is the GPT-2 training data. And so Python and SQL, they are also pretty large language data set. Okay? So language data all have words, right? So we first like embed the word into vectors using word-to-vector embedding. And then we take the feature trained by transformers as the feature to estimate intrinsic dimension. Surprisingly, the intrinsic dimension for this language data is not large. It's between 14 and 20. Okay? So I'm showing here the average of the intrinsic dimension we estimated from the data set. But in order to get this number, we need to take a lot of samples and do local intrinsic dimension estimation. So the geometric structure is actually more complicated. Well, Zai-Ming actually did more refined study. Well, he took tiny stories. So the data is pretty large. He just randomly subsample 5 subsets of the data. So you're seeing 5 results here. And for those 5 subsets, each of the subsets contain 100,000 tokens. And he estimated intrinsic dimension for that manifold. And then, so when we estimate intrinsic dimension, we need to pick base point, right? So, and then do local estimation. Actually, the result varies, saying that if you look at the first subset, the intrinsic dimension varies from 0 to like 30, okay? And then the orange is the mean, so it's between 10 and 15. And then this bar has the like 25 percentile and 50 percentile. Okay, so you can see that intrinsic dimension actually varies. So we get the average by the orange curve. So it does show that the language data has lower intrinsic dimension compared to the ambient dimension. So what are we going to do? We're trying to, as we said, we're going to trying to understand a little bit more about neural scaling laws, and we're going to connect that to approximation theory and some statistical estimation theory. And so here are some literatures. So there has been some approximation theory which relies a lot on the feed-forward part of the neural network, and we also heard in-context learning, which I'm going to talk a little bit at the end. And transformer scaling laws has been connected to intrinsic dimension by a paper by OpenAI. So for us, as we said, the power law is actually connected to the approximation theory. So we are going to establish approximation theory to understand the power laws. Okay. So we first consider regression of functions y is equal to fx. Okay. So this is called a single task regression because we just have a single function, and I'm going to assume that the function is supported on a low-dimensional manifold. It's a very smooth Riemannian manifold embedded in capital D-dimensional space. Okay, and then the manifold has a positive range. The function is nice. It's a holder function with holder index between 0 and 1. For example, s equals 1 implies that we have a Lipschitz function. Okay, so what is the range of the manifold? Maybe I'm going to skip, or we can talk offline. Okay, so for the single task regression, so we use the transformer architecture like this. So here, our input is a vector. Okay, so when we use transformer, we first have to embed everything into a matrix because transformer works on sequences. So we embed our vector x into a matrix like this. Well, it has 5 rows and many columns with some zero padding. So each of the entry coordinates in the vector is a token. And we are going to add the position encoding given by the cosine sine vector. So those are commonly used position encodings. So this position encoding is a vector which recognizes the location of the token. Okay? And so after we embed the vector into this matrix, and transformer will apply a lot of transformer blocks on this embedded matrix. So what is transformer block? So transformer block is a feed-forward neural network followed by multi-head attention. Well, the key is a single head attention. Okay? What is single head attention? So a single head attention operates a matrix with a value, key, and a query matrices. So you can see that when we have a sequence come in, we apply 3 linear combination by the value, key, query, and the key and the query will generate some score, and the output is the weighted sum of the value. Okay? So looking at this might be a little bit complicated, but if you look at the output, okay, for a specific token, if we use ReLU activation, and actually the output is a linear combination of the values, well, with weighted sum by the score. So this is really like kernel mechanism such that a token will interact with all the other tokens, okay? And then the interaction gave us a weight, and we are doing weighted sum for the output, okay? So using this mechanism, and so we are going to set up a network, transformer network architecture with some parameters. So when we train transformer, right, we need to specify how large the transformer is. So here we have some parameters. LT is the depth of the transformer, how many layers of transformer block we are going to put. So it's LT, it's an important quantity. And MT is the width of the network. So how many attention are we going to put in parallel in every layer? So this is by MT. And then transformer also have the feed-forward part, which we put the depth as LFFN. So when we use transformer, we want the feed-forward part to be small, okay? And usually we want very wide transformer. So like GPT-3 has 12 layers. So for transformer, usually like people use a wide and a shallow transformer with a lot of parallel attentions. And what's the advantage? When you have a lot of parallel attentions, you can do parallel computing. And that's easy for training, okay? And so I'm going to first talk about the approximation theory. So in approximation, right, simply, if we have a function, we would ask if the transformer can approximate the function, okay? So that's very simple, and we are going to consider function on manifold with Holder index, okay? So this is the theory established by Alex. So you can ignore many of the details, but I just want to tell you that we establish approximation theory by constructing a transformer network, explicitly constructed, to approximate a function f, which is a Holder function on manifold with Holder index between 0 and 1, okay? And so by construction a transformer, basically we constructed the key query and the value matrices to get this approximation. You can approximate the function with any accuracy, but smaller accuracy epsilon would require larger network. How large it is? So the good thing is that as epsilon decreases, the main increase of the size is on the width of the network. You want to increase the tensions in parallel as a polynomial, and then little d is in intrinsic dimension, okay? So I want to point out that the depth of the network is log intrinsic dimension is fixed, so it's not big. So our transformer depth is very small. Okay, in comparison, a lot of existing work use very deep transformers. And then the feed-forward part is also very small. It's like log. So which I want to show you that the approximation power is completely leveraged from attentions in parallel. Okay, we are not using feed-forward to do approximation. So this theory, if you rewrite it such that the network size is dominated by the width. So if you set this to be the model size, and then you get the approximation error, squared approximation error in a power law, where the power is given by the smoothness of the function s and the intrinsic dimension. Okay? So this is purely theoretical, but we did a little bit experiment on language models. So Alex is an expert on this. So he took some pre-trained models and then plotted the validation loss, which is the test loss, versus the model size, different model size, and different model size for 2 data sets. So left and right are 2 data sets. And then, so he got a result like the blue plots. So in log-log scale, it is actually linear, which is consistent with OpenAI's discovery. And so he just fitted the blue plots and then get the orange linear plot. This is the empirical fit, okay? And then he plugged in our theory. So what is our theory? Our theory says that the slope should be negative 2s over d. Well, s is the smoothness of the function, and we just use Lipschitz, S equals 1. And then D is the intrinsic dimension he estimated earlier. So it's not far, but it's not fitting the empirical law exactly. So this makes sense because the theory, you can see that the theory is better than the empirical results because the approximation theory is so good, it's constructed. Actually, approximation theory is better than practical result because practical result will have more factors like the statistical error and then the variance in the data part, which I will show you very soon. So actually, it makes sense like that the theory is better than the numerical results. And the generalization theory will consider data in the sense that the transformer is actually trained from the data. Well, you have n training samples, and you want to minimize some error according to this n training samples, and then get the global minimizer. Suppose we get the global minimizer, and we prove that the mean squared error, in the sense that you evaluate the transformer on a new data point x in the tested data, and then you integrate, this is the L2 error, and then the error is still random because training data is random, so we take expectation with respect to the training data. So we proved some power law saying that the mean squared generalization error should scale in a power law about the number of training tokens, little n, and then the power is negative 2s over 2s plus d, well, s is the smoothness of function, and d is the intrinsic dimension. So this error will be closer to practical applications because this is the result if you get the global minimizer in training. And so Alex did a validation for scaling law on the data size as well. Well, he increases the number of training tokens for 2 data sets. Left and right are 2 data sets. And he plotted the validation laws. Okay? And then the blue dots are the practical results, numerical results. Okay? So you do see a log-log linear relation. Okay? And so the green curve is our theoretical prediction. So what is the green curve? So green curve is a power law. Well, we plug in the slope like negative 2s over 2s plus d. So, well, as the smoothness, we don't know. We just plug in s equals 1 as a Lipschitz function. Okay? And then d is the intrinsic dimension. So surprisingly, the data scaling law actually, our theory is very close to the empirical result, which shows that the intrinsic dimension does play a role in the scaling law. Yes, and we did some ablation study for the intrinsic dimension. So the left part is about feature extracted at different layer of the transformer. So GPT, this GPT model has 12 layers. So we extracted the feature at every layer and estimated the intrinsic dimension. So it fluctuates a little bit from layer to layer, but not so much. It's still between like 10 to 20. And then the right plot is the intrinsic dimension with respect to the contact length, right? So when we do language data, so it comes up with a sentence, okay? And if you want to do the next token prediction, then we need to give a prompt, okay? So the right figure has the axis like the prompt length, 20, 40, how many words do we put in the sentence? Actually, intrinsic dimension decreases as the prompt length increases. So for language data, the longer you have the sentence, the more information we have, and then the smaller intrinsic dimension is. So those are just some evaluation studies. And I have 3 slides to illustrate the proof. So maybe I will skip now, and then I can come back if we have time. How much time do I have, Wenjing? 15 minutes. Okay, so maybe I still have time. Okay, so I will tell you how we prove this in pictures. Okay, so when we work on manifold learning, right, instead of the ambient space, okay, as we said that we need to respect the geometric structure. What is the geometric structure? So it's actually the local structure of the manifold. So for this manifold, our previous student, Mingshuo, developed a framework such that one can cover the manifold with a bunch of Euclidean balls. Okay? And then if we properly choose the radius of Euclidean ball, then we can project this local patch onto the tangent space and have a continuous inverse. Okay? And the reach of the manifold will play a role here in the sense if the manifold has large curvature, we want to have smaller radius. If the manifold is flat, like a hyperplane, then we can have a large radius. Okay? So the radius is given by reach over 4. Okay? After we localize on the manifold, and we are going to project a local patch on the manifold onto the tangent space. So we are going to use phi as the projection onto the tangent space. And as we said, if we choose the radius to be small, phi will have inverse. So in this way, we are doing dimension reduction to reduce all the points, project all the points onto the tangent plane, and then reduce the complexity from capital D to little d. Okay? So after you project to the tangent space, and then you can do all the approximation theory on the tangent space. Okay, so if we have spline or local polynomial, whatever, we can work on the tangent plane and have complexity depending on little d. Okay, so the main thing, the main contribution by Alex is to construct a transformer on this tangent plane to approximate the function. And the complexity depends on the intrinsic dimension. Okay? And so about the statistical theory, we use some standard machinery to split the mean square error into the approximation error, which is called the bias. And then the variance is some statistical error. Okay? And so for the bias part, if we can show that transformer can approximate the function, then we are done. And then the variance part is the statistical part. Well, we calculated the covering number for the neural network we use. Okay? So if you want to cover the neural network class with delta accuracy, and then the log covering number scales like log 1 over delta. And the key factor here is the width of the neural network. So MT is the width of the transformer neural network. So this is the dominant factor. So then you combine this to get the final result. Okay? So after this, I'm going to talk a little bit more about the multitask regression. This is collaborated with Rongjie's student, and Zai Ming, who is going to give a poster in the afternoon. So moving beyond a single function to multi-function, so we're going to consider in-context learning. So for example, we have a task of translating French to English. Okay? So we are giving a prompt, for example here, such that one already translated French word to English. Okay? And then for a new input here, the goal is to predict the English translation. So for this task, the goal is to make a prediction on a new input based on the prompt. Okay? And so now this thing is a training sample. So a training sample needs to have a prompt, because the prompt will figure out what task one is doing. And then you have a new input, you want to predict the output. Okay? So this has been mentioned by Hayden in the previous talk. Okay? So for us, we set up in a mathematical way such that we have two underlying distributions. So the input x now is randomly sampled from a manifold. And then we have a function space. Instead of learning a single function, now one needs to learn multiple functions randomly sampled from a function space, like the holder function space on the manifold. Okay? And then the training data will involve multiple tasks, such that one task will have the prompt, the input, and also the output. So those are the training data, where we use gamma to index the training data. So capital gamma is the number of training tasks we have seen. Okay? So for this problem, it's naturally to ask the question, so if we use transformer or any other neural network, what is learned by transformers, right? So as we said that transformer is going T theta, is going to learn the output based on the prompt and also the input, okay? How does it learn? It's going to learn from the training data. Well, each of the training tasks will evolve a randomly sampled function in a function class. And then you're going to test it on a new function, okay? So this is very important in the sense that, so the training data say different functions. Now we are not learning the function itself, because learning those f gammas has nothing to do with the prediction on f, okay? So what is learned by transformers, and we learned from the paper Transformers as Algorithms from computer science community. Well, they claim that for in-context learning, transformer is learning an algorithm instead of functions, okay? So what is the algorithm? So now I'm going to list as a simple algorithm, kernel regression. It's an algorithm such that if we have a lot of prompt and then also a new input xn plus 1, okay, how do I predict the function here? I can do a local kernel average to average out the functions around this point and then weighted by this kernel. So this is the algorithm, okay, such that we want to learn the interaction of them and give the output. Okay? So our main work is to connect transformer in with kernel methods, okay? Such that for in-context learning, we are going to first embed the prompt into tokens, and also we are going to put a new input in the next token. So for all the previous token, we have the answer, the output. But for the new token, we don't have the output. So the question mark is what we want to predict, okay? We are going to use position encoding as well, which is very important, okay? So we first construct a transformer using the interaction mechanism in the attention with ReLU activation function to make xn plus 1 interact with all the previous samples, x1 to xn. And this interaction will give rise to some weight giving where we store in the matrix. Okay? And next, we are going to use attention with softmax activation function to do some weighted sum, which gave rise to the kernel method. So the output here is given by the Gaussian kernel between xn plus 1 and all the previous samples, and the weighted sum of the function, well, the weight is given by the Gaussian kernel. Okay? So this is all by construction in the sense that we constructed a neuron transformer to realize kernel method. Okay? So in practice, we cannot come up with the neural network which we constructed, right? So one has to do training in the sense that you are going to set up a network with certain depth and width, and then this transformer is trained to minimize the prediction error for each of the training data. So we're going to do prediction for the input based on the prompt, okay? And after you train the transformer to get the global minimizer t hat, we're not addressing any optimization here, and then we are going to use t hat to make a prediction on a new test sample, which has a new function, okay? And then, so what is test error? So we are going to look at the error, okay? Statistically, this error is random, but we're going to take a bunch of expectation, saying that we are going to look at test sample and look at many test sample and average. So this expectation about the test sample. And then we are going to take an expectation about training sample, saying that what if we have more and more new training samples, okay? So our main result is the following error bound, saying that if you get a global minimizer t hat and you use it to predict a new task, the mean squared error is going to have two parts, okay? So, well, the second part, little n, is the prompt length, okay? So when I'm going to predict the new function f, we are going to give some prompt. So this n is the prompt length. And so the second error, n to the negative 2, sorry, this is typo, s over 2s plus d, is actually the min-max regression error for functions on manifold. And the first part is new for in-context learning in the sense that, so transformer need to learn an algorithm to make prediction for f. So the sample complexity of learning the algorithm scales like 1 over something square root over square root gamma. Well, gamma is the training task. So this part is saying that if you see more and more training tasks and you are going to make the algorithm you're going to learn the algorithm better. Sorry. So this is our main result, and we did some numerical experiments. So, well, we take the manifold as the 2D sphere embedded in 3D, and we take the function class and some linear combination of the spherical harmonics, okay? And then we want to test the scaling law about the prompt length little n, and then the training task number gamma, okay? So first, we look at the scaling about gamma. The left and right curve are the same, but we do log-log scale in the left and regular scale in the right, okay? So if you ignore the second term, and then we should say something like gamma to the negative 0.5, which is given by the red curve. But because of the second term, right, so it actually decays like a little bit like gamma to the negative 0.5, but then the error is actually limited by the second term, so it does not decrease that fast anymore. Okay, so this makes sense, right? Because the training function and task function are different. You need to see enough prompt for the task function in order to figure out f. Okay, and then we also fix the gamma. Gamma is 400, 1600 in the left and right, and then now we check the different n. So interestingly, if you look at the scaling about n, the prompt length, it's hard to tell because these two terms are different. So the first term is like n, the second term is like n to the negative power, right? So what we see is that if gamma increases, it will actually suppress the first term, and then you get a faster rate of convergence. Okay, that's the end of my talk. So as a summary, we did a little bit approximation and generalization theory and try to use the intrinsic dimension to explain neuron scaling laws. But there are lots of things to do, like the optimization, which we did not address at all. And for the in-context learning, we understand transformer as learning an algorithm, and we characterize the complexity of the algorithm learner. Okay, so that's it. Thank you very much.